So, dear finalists, dear jury members, and everybody else who would like to see the presentations. My name is Jānis Klive. I'm a vice president of CLGE, and I'm responsible about this organization of the CLGE Young Surveyors Contest. So this is the final stage of Young Surveyors Contest, and today we will see presentations from the 6 presenters in each category. One category is for Masters and Bachelors degree, and second is for doctoral degree category. So just to inform you, we will record these presentations, and afterwards, if everything will be fine, we will present them in our publishing our CLGE webpage. So in case it seems very interesting for you, you could follow also afterwards. So I will start with short presentation from my side. I will describe a little bit about CLGE and the contest itself, and then we will come to the finalists. So I will share my screen. I hope you can see it. Yes. Marinelli, can you hear me as well? Marinelli Dancho is on my, yes, we will organize this session together, so we will try to do our best. So this is a already 12th edition this year. And as I said, I will start with short introduction about CLGE as in general. So usually we use this acronym CLGE, but for everybody to know, that full name is Council of European Geodetic Surveyors. And we are leading surveyor association in Europe. So for everybody to understand that we're gathering together all associations in every country in Europe, and not only associations, but also some organizations and cadastral organizations and such. So totally we have 38 member countries, 3 observing member countries, and also 27 European Union member states. Totally, we're gathering more than 100,000 surveyors in Europe. And also, we have a close cooperation with other organizations in Europe and worldwide. CLGE Student Contest already starts in 2011 and 2012, and this was just at the beginning. And at the moment, we change our name, not a student contest, but Young Surveyor Contest, to make it closer, maybe to FIG, meaning for Young Surveyor. This year, we got 30 applications, very good. And on the screen, you can see also statistics by the countries. We have 5 from Bulgaria, 4 from North Macedonia, 3 from Spain, Poland, and other countries as well. So widely covered, and we are happy with this. On this map, you can see the total number of papers from previous year. This year it's not yet summarized because we don't know the winners at the moment, but you can see the darkest countries are with the most students or papers from CLGE Young Surveyor Contest. And on this map, you can see also the winners. It's a close correlation with the numbers of applications. So Germany is at the top at the moment, and also following Latvia and other countries. I will start with gratitude to our ambassadors. of the contest. They are promoting this contest amongst the colleagues and our ambassadors. They are winners from previous year, and this year we had 4 ambassadors from the last year. It's Susanna Cypers, Dogus Guler, Asnata Egle, and Miloš Tunjevic. And now I would like to say also thanks to our jury members, and also for others. I will introduce the jury members. Totally we have 7 jury members, 3 from the industry. So first is Bernhard Richter from Leica Geosystems. Then comes Anna Maria Luango from also space company, and Paul Chambon from Hexagon Terrier from French company. The next we have 2 jury members from universities. So it's Leiv Bjarte Mjøs from Western Norway University of Applied Science, and Nele van Hout from University of Applied Science in Ghent, Belgium. And at least we have 2 from CLGE. As I introduced before, it's Marinelli Dancheva. She's Young Surveyor representative to CLGE. And me, myself, Jānis Klive. So what's the goal today? It's prizes, and on the recommendation of the juries and in the name of the CLG, we will bestow the prizes at INTERGEO fair. And the first prize is at 1,500 euros, second and third, as you see on the screen. So this is for the winners. But despite this contest, I would like to say that all of the finalists are very good, and you have to be proud by yourself. And whatever of these results, keep on going, and everything will be fine. So, and the awarding ceremony will take place in INTERGEO. This year it is in Stuttgart, and everybody is welcome to participate. And here you can see some pictures from the last year. And then I hope some celebration will be also this year. So everybody is welcome. So, and now we come to the final few pages from me, that we will start with bachelors, about 1 hour. We will see presentations from Angelina, Juan, Miloš, Cynthia, Pavel, and Mazil. And after each presentation, there will be possibilities for the jury members to ask some questions. If not, then we will move to the next presenter, and so we will see all 6 presentations. Then for half an hour, we will have a break, and jury members also will meet in another room to discuss about these presentations. And then we at 6 o'clock from the Central European Summer Time, we will see next 6 presentations from Antonio, Erki, Juan, Camille, Marroca, and Natasha. So this is a plan for today, and thank you for attention from my side at the moment. So you can follow us also on our webpage and social media and so on. Before we start presentations from Angelina, I will say that all the participants will show the presentation in Pecha Kucha style. So it means that everything will be equal conditions for all the participants. They will speak there will be 20 slides per 20 seconds. So totally it will take some less than 7 minutes for every finalist. So good luck for the finalists, and let's enjoy the presentations. Can
you fully see my screen?
Yes, Marinelli, that's okay. I can see your screen. And I can start to introduce our first finalist. She's Angelina Jerjomina from Estonia, Tallinn University of Technology. And I will ask Angelina, do you hear us? And open your mic.
Yes, hello, I can hear you.
Yes, very good. So you have to be brave one, yeah, to start our session. And are you ready?
Yes, I am.
Yes, so Marinelli, you can start your presentation.
All right, good afternoon to everyone. My name is Angelina Jerjomina, and today I want to present you my master thesis topic, which is surveying of underground networks using low-cost LiDAR sensor. Currently, I'm a student of Tallinn University of Technology in Estonia. I finished almost all of my studies specializing on construction surveying. During the studies, I was working in construction surveying company, Thesis Geodesy, and I have 4 years of experience as a construction surveyor. Currently, I am also finishing the internship at European Space Agency, developing the methodology of mirrors measurement and alignment using lasers radar. The measurement of underground utility network is a very common work for surveyors. Due to tight construction schedules, usually the trench is closed right after the pipeline's installation, and unfortunately before the surveyor arrives at the construction site. In this case, it is not possible to measure installed pipelines directly, and it can bring a lot of inconvenience in quality of data and therefore in the future use or renovation works of the pipelines. 4 experiments were conducted to test low-cost LiDAR sensor capabilities for pipelines measurement. First experiment was performed in indoor conditions with different types of pipes varying in diameters. The next 3 experiments were performed on real construction sites using the knowledge received from first test. One of the goals was to determine easy-to-use measurement methodology fully suitable not only for construction surveyor, but also for the contractor. The iPad Pro with built-in LiDAR sensor and 4 different third-party scanning softwares were tested. The softwares were Scaniverse, VGS Scan, 3D Scanner app, and Sidescape. The reference system of each experiment was established using a total station with mini prism, and in outdoor experiments also RTK GNSS receiver was used. For point cloud comparison, the terrestrial laser scanning was performed on each test. Additionally, in every experiment, some of the pipeline's elements were measured using total station. The indoor experiment was performed in 3 different parts. First part, movement trajectory moved around the survey area with LiDAR sensor pointing in the center, while second and third trajectory moved in between the pipes. The height of the sensor was stable during first and second part of test, but during the third test it was varying. For all 3 outdoor experiments, the reference points using RTK GNSS methodology were measured to coordinate the LiDAR point clouds independently from total station measured reference data. The trench of outdoor experiment 1 was approximately 3 meters deep, and the measurement was performed in 2 parts, outside and inside of the trench. The movement trajectory of the second outdoor experiment was moving around the trench, starting and finishing approximately in the same location. In first outdoor experiment, the sewage and the water supply pipelines were measured, while in second outdoor test, the pipes for electricity cables were measured. In third outdoor experiment, again, the severe pipeline was measured. The movement trajectory followed the pipeline inside the trench. It was possible to capture the pipeline by walking only in one direction because the trench was shallow and quite narrow. The Cloud Compare and Autodesk softwares were used for data post-processing. On the figure, you can see the statistics of discrepancies between low-cost LiDAR surveyed and terrestrial laser scanning data. The graph shows that Part 2 measurements have better results with almost all scanning softwares. On current figure, you can see the cross-sections of one pipe with diameter of 110 millimeters. From this figure, it is also clearly seen that Part 2 movement with regular walking speed and slaloming trajectory is giving the best result of pipe geometry. On the next slide, I would like to draw your attention to the top right table that is showing the determined slopes of gravity flow severe pipelines, and it is clear that the LiDAR measured slopes are showing similar results as total station or terrestrial laser scanner measurement. the statistics of discrepancies between LiDAR surveyed and terrestrial laser scanning point clouds are showing that the root mean square errors in all the outdoor experiments and almost with all the tested scanning softwares stays in between 2 and 6 centimeters. Although the point clouds captured by different applications are still quite different, as you can see on the figure. The next 3 slides will show the visualization of discrepancies of low-cost LiDAR scanned point clouds relative to terrestrial laser scanning ground truth. On the right, you can see 3 colorized point clouds. The first one is captured by Scaniverse, second by VGS Scan, and third by a 3D Scanner app. On the left, you can see the section view of the LiDAR measured data with different softwares. Section views were created in Autodesk Civil 3D software. In outdoor experiment 1, the manhole and the part of sewerage pipe is shown. In the outdoor experiment 2, the section view is depicting the part of pipes that are meant for cables to come out from underground and create the connection inside of the future building. In the outdoor experiment 3, the section view of 2 potential connections of severe inside the building is represented. On the next slide, we'll show the resulting point clouds of the measurements that were performed by contractor. He received the training of operation with instruments and softwares by the surveyor. The reference system for each scanning was established by contractor using the RTK GNSS measurement, and then pipelines were scanned using low-cost LiDAR sensor and Scaniverse software. This data was later used for the as-built documentation to create as-built drawings and models. As a conclusion, I would like to say that the low-cost LiDAR measurement is in cooperation with RTK GNSS measurement is accurate approach for underground utility networks measurement, at least regarding Estonian regulations, and also easy enough to implement this methodology by the contractors without the construction surveyor education, but with proper training and the support of the surveyor. This will solve the problem of more complicated planning and reduce the amount of data with poor quality. Thank you for your attention, and if you have any questions, then I will gladly answer them now or later.
Thank you, Angelina.
Thank you, Angelina. Yeah, that was very good. At the moment, I will ask jury members. Maybe they have some question at the moment. For jury members, so if you want to ask something, you just open your mic and ask.
Just a quick question. The referencing is always done via control points, right?
Yes.
Okay, so it's a relative accuracy always when you say it's within your project, you say it's within 2 to 6 centimeters accurate, correct?
Yes, correct. And for indoor experiments, the reference points were measured. The reference system was established using the total station measurement. And for outdoor experiments, I was using the GNSS measurements for the LiDAR. And for the terrestrial laser scanning, I was using the total station to compare them and to see if it is possible to achieve the accuracy, well, the precision. We also were using the RTK GNSS measurement like as a reference points. So basically, to contractor, if like the total station is much more expensive and also much more complicated methodology to use, so it is more easy to train the contractor to measure with the RTK GNSS, and it is also cheaper for them, so they can purchase it or yeah, and yeah. So the goal was to see if it is possible to achieve this accuracy with GNSS RTK.
Thanks, understood. Our total stations are not complicated and not expensive, so
yeah.
Just to check.
Okay.
I also have a small question.
Yeah.
I would like to ask you if it's mandatory by the government in Estonia to measure the position of underground pipes.
Yes, it is. We have regulations. On the one before the last slide, there were some of the regulations shown that the planar position should be determined within 8 centimeters, and the depth of the pipelines should be, I think it was 3 centimeters plus the amount of depth of the pipe. But yes, it is mandatory to measure them and also to upload the as-built documentation, the drawings in the specific place to store this data.
Okay, thank you, but not by a property surveyor. It's not mandatory that the property surveyor measure the position.
So
I'm not
difference
sure
is some property surveyor or a geodetical surveyor. That's the question.
I am not sure what is the term of property surveyor actually.
Okay, no problem.
So okay, land surveyor. Mm-hmm. Okay, thank you, jury, for questions. I think that's it. So thank you, Angelina. We go to the next presenter. It's Juan José Valero Lanzuela. He's from Politécnica University of Valencia, Spain. So Juan, are you ready? And yes, your mic is ready. Yeah, can you speak a little bit louder?
You can hear me?
Yes, but with some disturbance.
Can't hear very well, to be fair.
Yes, okay. So
No,
yes,
no, I cannot.
You cannot hear me.
It's very, very low.
Okay.
low,
And now?
slightly better.
Okay. I just restart the mic.
No, it's okay. It's okay. Just start. So
Okay.
you are ready, yeah?
Okay.
Okay, Marinelli, you can start.
Hello, everyone. Hello, the contest committee. My name is Juan José Valero Lanzuela, and I'm glad to meet all of you for the first time. I will start speaking about my final degree thesis about the identification of real estate properties in financial assets management in Spain. First, we have to review the structure of the property management in Spain. There are two administrative bodies for real estate control: the Cadastral Office, which handles economic control for tax purposes, and the Land Registry, which provides legal guarantees for the land or the property ownership. During 1997, in Spain took place a real estate boom, and a lot of new buildings were not legally registered. In 2007, Spain was hit by the explosion of the bubble of the brick. Construction companies go broke and banks begin to execute mortgages massively. The Spanish government created a fund for orderly bank restructuring, the FROB, to address the crisis. The FROB aimed to absorb toxic assets from the bank's balance sheets, helping to clean up their accounts and establish the banking sector. To solve the inconsistency of having two organisms that work separately for the land control, Spain published the Law 30 of 2015 to reform the mortgage law and the real estate cadastral law to obtain the full coordination between the registral information and the cadastral information, giving graphic support to the registral land and legal guarantees to the cadastral information. Since then, the FROB itself created the Sareb, who is popularly known as the Bad Bank. They are still working to regularize and reintroduce the assets to the real estate market, but there is a lot of work remaining. In 2019, I began working at a company focused on identifying those real estate with issues. My roles involved investigating and preparing reports to help banks link financial assets with registry inscriptions, legal documents, and cadastral information, even maps. The proper identification of the assets is needed before any other legal processes, even to regularize the asset situation, to make an appraisal or an evaluation, to estimate cost, or to sell it without any kind of doubt of what you exactly own or what you exactly are selling to others. As I mentioned before, there are multiple administrative entities for real estate control, each one managing different aspects. The information is complementary, providing various perspectives that together approximate the actual reality. I'm going to explain a real example of how from a 1920 description we can obtain its relation with the map on the right. The image on the left shows the registral documentation. Since then, the description of the land and the titularities were not notified to the authorities up to 2019, when the bank got the legal rights over it. From the registral documentation, we can resume the image on the right, a transcription that contains the registral number, the toponymic relevant information, its surface, the fourth cardinal boundaries. And as you can see, there are 3 roads. This is because this one registered land with 3 parts. Once the toponymia has been extracted out of the registral documentation, we can go to the historical archives and retrieve the documentation of the taxpayers in this location. Resume this information in tables and look for coincidences with the boundaries related according to the registral documentation. The first map we took was from 1914 and is similar to the newer one, except the parcels 100, 123, 124 that had been merged into a new one, the 140, and it seems someone combined them without notifying the land registry. At the end, comparing the data extracted from the registry and the cadastre, we can correlate the surfaces of those 3 registered portions of land with those old parcels, and then with the current ones marked in red. In other examples, it's much harder and expensive to do, but the methodology is pretty much similar, but with larger tables. This example shows the identification of 55 assets in a touristic area called Cullera. That was a lot of work. Some conclusions we can extract of this is that the Law 30 of 2015 does not require an identification report, but it's highly recommended. The most time-consuming tasks are finding the documentation and performing the toponymic analysis on actual maps and older maps. There are a lot of work we can still improve. For example, is still needed a lot of digitalization of historical documentation. Traditionally, accessing most documents requires a fee, but making them free and online will save time and money for everyone, even from the administration. As mentioned, finding toponyms is time-consuming, as place names often change over time. I've been working in toponymic recognition using multi-language large models with artificial intelligence, and so far I have been promising results. There is a bit more work apart of the toponymic recognition, but it's not as hard as the main problem, and I already identified some of the next steps of this future job that involve also public administration and contact with authorities to serve the solution online. Thank you. I want to thank you everyone for the opportunity to be showing my work and my interest, and I will try my best responding your questions, if any. Thank you.
Thank you, Juan. I just want to mention for everyone that amongst all the finalists, Juan is the only from bachelor thesis. Yeah, all the rest is from master thesis. Yeah. So now is the time for questions for the jury. Okay, it seems no questions. So thank you again.
Thank you, everyone.
And we can move on with the third presentation from Miloš Basarić, and he from Serbia, from University of Novi Sad. Miloš, can you speak? Are you ready? We don't hear you. Just try again, maybe open your mic. Sorry, we don't hear you. So my proposal, maybe Miloš, you can restart your computer or join us again, and maybe we can move to the next presenter. And Cynthia, are you ready?
Yes.
Okay, so I will introduce you, Cynthia Okeke Ogachukwu, and she's from University of Applied Science from Stuttgart, Germany. So she's yeah. So Cynthia, are you ready? Yeah.
Yes. Yes. Thank you. Okay. Good afternoon, everyone. My name is Okeke Cynthia, and I'm here to present my thesis topic, which is utilizing deep learning to categorize buildings according to their construction year from mobile photographs. One of the global strategies that we are facing right now for energy security is to reduce energy demand and consumption, and the research has shown that the older the buildings, the more energy it demands and consumes. The accurate estimation of building ages is crucial for urban planning, energy efficiency assessment, and sustainable development. And that is why the research comes in to present a deep learning methodology designed to accurately predict building age information from mobile photographs. According to the tech company which I partnered with, they say that for them to calculate energy demand and consumption, that they need two parameters, which is one, the construction year or age of the building, which where my research focused on, and the second one, the energetic parameters of the buildings. And this is a case study whereby we want to solve the problem of estimating the building age from photographs. The research aim was to utilize deep learning techniques to estimate the ages or construction years of buildings in specified study areas. The objectives include to categorize buildings according to their year of construction using pre-trained models, and to develop a model with the ability to forecast building ages. The study area for this includes some neighborhood or residential neighborhoods or districts in Baden-Württemberg, which include Leutenberg, Almedingen, and Kirchdorf, etc. This data collection was also improved by additional features, which include the GML ID of the buildings, the GML ID of the buildings, the construction year of the building, which has the label from 0 to 7, and the building images, the mobile building images taken by the professionals. With these features, we are able to now categorize these buildings together. But before we do that, one of the things that we also progressed to do was to make sure that these things are aligned together. According to Institute for Wohnen und Umwelt in Germany, every building area has common construction methods, but also typical component areas, such as window sizes, that have a significant influence on the heating demand. As you can see on the image, there are some buildings built in different building construction area, 1860 to 1918. Also, according to the Institute for Wohnen und Umwelt, the German building stocks are divided into 12 classes, from level 0, which started from 1859, to level 11, which stopped at 2016. But because of this, my research, it was meshed together, and the classes were coined around Germany historical periods, which are pre-war, post-war, prosperity, and the other. Data preparation was done to remove the obstructions such as cars, trees, shadows, street lights, and all of that, to make sure that the photographs are good or great enough for the model training. Then for the model training, the model development I used were two methods. The first was the transfer learning by fine-tuning. The transfer learning by fine-tuning involves freezing the pre-trained model weights and training only the new layers. And for this particular model development, I used the VGG16, which contains 16 layers. And for that, it was also, I also used divided the data set I got, because the data set I got was 1,738 images. 1151 images were used as training data set, 294 as validation, and 293 as the evaluation. Looking at the table, you could see how they were all classified. This was also going about using the 70%, 15%, and 15% as training, evaluation, and validation. On the analysis, you can see the parameters I used during this model development, and it was not efficient enough because it was only one class that got results. The other classes did not have any results, which made it to understand that the transfer learning by fine-tuning was not great for my data set, which is the mobile photographs. And because of the limited data set that I have, so fine-tuning is often beneficial when you have a moderate to large data set for your new task. That is why I now changed again to another transfer learning method, which is transfer learning by feature extraction. Transfer learning by feature extraction involves freezing the pre-trained model's weights and training only the new layers. For this particular one, the pre-trained model used were ResNet 50 and efficient net models. These are the pre-trained models for specifically mobile photographs. Using this, I was able to compare the ResNet 50 and efficient net models to know the one that will give me a better accuracy. Comparing the two of them, you could see that efficient net on the table, efficient net gave me a better accuracy of 30%, while ResNet gave me accuracy of 24%, and it also produced results on the classification reports for the two models. And that made me to realize that this particular transfer learning is great for this kind of project. Then the summary of transfer learning by feature extraction is that it is beneficial when you have a small data set for your new task, as it avoids overfitting, and also only the final layers specific to the new task are trained. For this, we are now went straight to evaluating the difference between the transfer learning method by fine-tuning and feature extraction. Looking at this image, you could see that the learning curve does not depict or could not even diagnose the behavior of the model, which made it not to be very efficient or effective for this particular training or for this particular data set. Then additionally, the evaluation, the feature extraction method, the training curves depict or the training curve proved sufficient for diagnosing the model's behavior. When comparing the two models, the classification reports provided comprehensive results as well. And as well, EfficientNet produced more accuracy because of the different analysis I have done. It's produced more accuracy more than the ResNet. Looking at this as well, you could see the images that they predicted the same, but looking at the ResNet 50, you can see that it's predicted only 2 compared to EfficientNet that predicted more than seven correct buildings. This is one of the samples of or examples of the image I screenshot. Then the conclusion. In conclusion, this research has effectively met its objective by categorizing buildings according to their construction years and successfully developing a model capable of predicting or forecasting building ages from mobile photographs. Nevertheless, this study also confirmed that it's critical to increase the data set. Thank you. Thank you for your attention. Any questions?
Thank you, Cynthia. Keke.
Thank you. Thank you.
Yes, it was in big studies and interesting topic. But for me, I will start with some question already. Can you give an example how you can characterize some characteristic to predict what is the year of the building? It could be renovated.
Yes. So for this particular research, we decided to remove the concept that the building might be renovated. But for the upcoming research that we are on right now, we want to include whether the buildings might be renovated, because we have the data already. The ALKIS data set from Germany, but from Baden-Württemberg, which the Steg company has also improved on. So we want to also include whether the buildings have been renovated. But this very first start, we want to make sure that the idea for predicting building ages from mobile photographs is very possible. So this is what we did with this project.
Okay, thank you. Maybe more questions from the jury? Okay, there's no questions. Okay, thank you. Okay.
Thank you.
So we will try again with Miloš. Miloš, can you try to open your mic? Unfortunately, we don't hear you.
I suggest that you can transfer probably the code to your phone, or duplicate the code through your phone and maybe try this way.
To open also the application from mobile phone, Teams.
Or alternatively, if you are using browser, try app, or if you're using the application, try the browser.
Can you hear me now?
Yes, yes,
Yes.
finally. That's
Perfect.
good.
Okay.
Okay, so mic is working. So Miloš, are you ready?
Okay, we can start.
Okay, good.
Okay, so hello everyone. My name is Miloš Basarić, and I'm very happy to be here. I will present to you my research, which is my master thesis from 2022 about automatic generation of building data from satellite imagery for the production of the topographic map in a scale of 1 to 25,000. So to introduce myself, I'm military educated geodetic engineer, which has shaped my approach to this project. And currently I work as a junior researcher at the Military Geographical Institute. And I'm also PhD student of geoinformatics at University of Novi Sad in Serbia. So large-scale maps, such as topographic maps, contain a great amount of data and a large number of map sheets. So their production can be very demanding, especially in urban areas. On this type of map, buildings are mainly represented by points, lines, and polygons, cartographic symbols. So in urban areas, the most dominant symbol is non-scalable point symbol for buildings, which is represented in the corner of the slide. The automatic generation of this symbol is actually the subject of this research. The symbol can appear tens of thousands of times on some map sheets. Traditional methods of data collection and cartographic design based on satellite imagery are time-consuming, which is particularly challenging in areas where the national spatial data infrastructure has not been implemented, and therefore finding ways to collect data more efficiently is highly justified. So there are strict rules for displaying building data. The minimum distance between two symbols is 5 meters. It's important not to display every object, but only those that visualize the character of the settlement. And finally, those symbols should be placed snap to higher order roads and separated from lower order roads. This research represents the application of deep learning for binary segmentation of satellite imagery with a resolution of 30 centimeters and the use of algorithms specially developed for this project to convert segmentation mask into cartographically usable data through vector processing. So accordingly, the methodology has two components, one focused on the building recognition and the other on vectorizing, processing, filtering, positioning, and generalizing data to make them suitable for use on topographic map. All the processes are based on Python. So image segmentation was carried out using the UNet convolutional neural network, originally developed in 2015 for biomedical image segmentation. This network has proven to be an excellent solution for object recognition in satellite imagery in recent years. The UNet network was trained on the Open INRIA dataset, which consists of 30 centimeters resolution satellite images and corresponding ground truth data, which match the resolution of the input satellite imagery intended for this research. And the model was trained in 60 epochs. So starting from the satellite image, a building segmentation mask was generated using deep learning model. The mask was vectorized into polygons. The polygons were simplified and their directional angle was calculated. Non-scalable building symbols were placed in the center of the polygons and rotated according to the calculated angle. The generated symbols were further processed. In the first image, rotated in the direction of the nearby roads. In the second, moved closer to higher order roads. In the third, moved away from lower order roads. And in the fourth, they were generalized and sparsed in accordance with the minimum distance of 5 meters. The output results require minimal manual correction, significantly speeding up the creation of building data for one map sheet. It can be said that the obtained results are semi-finished products. So The next image, this image shows a segment of a city where the data were obtained. As I mentioned, these data require verification by an expert, but the time required to correct and verify the data is significantly less than creating these building data from scratch. High accuracy of deep learning model is desirable, but extreme precision isn't essential since the data will be generalized with point symbols. The key is for the model to maintain building orientation for accurate differentiation on the prediction mask. On this segment, an accuracy assessment of detected building data was performed using confusion metrics, which show a high accuracy of around 90%, confirming the usability and cartographic accuracy of this data. This methodology has been implemented in a topographic map production system at the Military Geographical Institute and has achieved positive results in practice. Given that it was implemented in an offline environment due to work policy, I wanted to emphasize that this process was extremely demanding. Implementing a deep learning environment offline was uniquely challenging due to numerous Python libraries and dependencies. Ultimately, a building recognition for about area of 120 square kilometers of satellite image is generated in about 4 hours, and automated vector processing lasts about 30 minutes. Overall, this changes in process for creating topographic map at the scale of 1 to 25,000 has accelerated the production of a single map sheet up to 30%. And this contribution is significant and noticeable. So the idea for the future work is to apply the methodology to other types of data, such as, for example, vegetation and roads, and to use deep learning satellite imagery segmentation to create new cartographic data that will contribute and improve the process in topographic map production across all fields. So that's all. Thank you very much for your attention.
Thank you, Miloš. Now it's the question time for jury. Maybe have some questions.
Hello, I have a question. And
Yes.
it's related to the satellite imagery. Which kind of images you used in your analysis?
Excuse me, can you repeat the question? I didn't hear
The-
it well.
The question is what kind of data set you used for your analysis? The satellite imagery, very high resolution satellite data.
Yeah, if I understand the question correctly, the question was what type of satellite imagery I used as an input data.
Yes.
Okay, so that's WorldView 2, 30 centimeters in spatial resolution, and it's just 3 channels, R, G, and B.
Yes, I think so. Yeah, correct.
Maybe just one more question.
Yes.
Did you make also a comparison in terms of accuracy of the position of the element that was identified? Again, coordinates or something like that? Were you able to make a comparison in terms of coordinates of the elements that you identified? Was it well positioned or not in comparison with maps or something like that?
So the question was if there was a comparison to
yes,
run through data on the topographic map as a final data.
Yes.
Yes, there was a little study. So we put up some kind of a race. So one group of people did small amount of small area by doing it as previous, and one group of people done it with this method where you have semi products and you just have to verify it and to correct it a little bit. So let's say we did this racing type of verification, and in that way we conclude that we will save a lot of time by doing it in this way I proposed in this research.
Okay.
I hope that I'll made it a little bit clear.
Okay, thank you. Seems over with the questions. So thank you again.
You're welcome.
Miloš. Yeah, and we can move to the fifth presenter. He's from Poland, Paweł Czernik, and he's from Warsaw University of Technology. So Paweł, are you with us?
Yes. Hello. Yes.
Hello.
Do you hear me?
Yes,
Okay,
very well.
Perfect.
So are you ready?
Yes, I'm ready. Hello, everyone. My name is Paweł Czernik, and I'm from Warsaw University of Technology, Poland. In this presentation, I will show you the results from my master thesis. This thesis was written during my work on the European sitcom AI project. So let's start. Initially, I would like to focus on the workflow I developed that allows tracking pedestrians with CCTV cameras. The workflow consists of two main parts: computer vision, the upper one, and deep learning, bottom one. I will discuss the individual steps in the following slides. As for the input data, it was footage from 6 surveillance cameras on my university campus. The recordings were from different times of the day and the year, which is important for training neural networks. We can see position of the camera on previous slides. To make the camera recording useful for further processing, it was necessary to calibrate cameras with a chessboard and then using the OpenCV library to obtain the camera and distortion matrices. Measuring the transformation points in the photo and in the global coordinate system was necessary to perform the transformation. For this purpose, I used total station measurements based on the benchmark established with an RTK. During the research, I decided to test 2 transformation methods. The first was DLT, direct linear transformation. I used the singular value decomposition method to calculate the transformation parameters from a homogeneous matrix. However, this method is not optimal due to the distribution of measurement points on a quasi-surface. In the best case, the RMS error is 1.1 meter, so I decided to try perspective and pose computation. As we can see, the results of this transformation method are better than the results of DLT, especially for a distance of 20 to 30 meters from the camera. We can achieve position accuracy of less than 1 meter, which satisfies my expectation. With this transformation, we obtain a matrix P, which, when transformed, allow us to obtain formulas to convert any point from the photo to the global reference system. These formulas are written in Python, and this is the end of the computer vision part. Now we can go to the part connected with deep learning. I decided to use YOLO V8 from Ultralytics because it's fast, accurate, and easy to use. I used the web-based CVAT tool to annotate pedestrian and camera frames. The results of the data annotation was a unique text file for each frame, in which the coordinates of the center of each bounding box and its dimension were marked. All coordinates are relative, adapted to a particular image. Here we can see the number of frames and objects along with a split between training, validation, and test data set. I marked, as you can see, a lot of pedestrians, but this is not a large data set if we discuss in neural networks. At first, I started training the neural network using only CPU. However, after first epoch, I found that it would be necessary to implement a GPU-based solution. This made it possible to reduce the training time by about 25 times. In the end, I trained two models, nano and small. With the medium model, the training time increased drastically to several days, so I decided to use only these two. In both cases, MAP 50 is about 90%. Using trained models, the 3-hour-long camera's footage was analyzed. As a result, pedestrian and individual frames were detected. Correctly converting their position to the global reference system required moving the detection point to the center of the bottom of the bounding box. After success with pedestrian detection, I expanded detection to include tracking. This allows me to assign a unique ID and record the trajectory of individual pedestrians. As we can see, this network can deal with multiple tracking effectively. The detection results were saved to the CSV file with unique ID, image coordinates, and confidence. Then the transformation functions I mentioned earlier were applied to them. This process was done using Pandas library. The final result are CSV files with global coordinates systems. Here we can see sample of geospatial analysis performed in ArcGIS Pro from a simple display of detection points through individual pedestrian trajectories, finishing with pedestrian movement heat maps. I decided to draw attention to this analysis because we can see here the false impression that the most pedestrians use the street. But the pie chart analysis shows that pedestrian traffic is mainly on the sidewalk. And thank you for your attention. I could have talked about it for half an hour, but the presentation format forced me to shorten it in such express form. If you have any question, feel free to ask. Thank you very much.
Okay, thank you, Pavel. Yeah, it's quite complicated topic you have and interesting as well. So maybe jury has some questions.
I'm just wondering if you would have lots of elevation differences, would that make it more complex for the positioning?
To be honest, in Warsaw, we don't have a lot of difference in height. So I assume that I transform from photo to the only X and Y coordinate.
Okay, so you're global. Basically computing a plane, is that?
Yeah.
Okay, I got it.
But it's a good question. I never wondering about it. I must think about it free time.
Continue studies.
Yeah, I hope so.
For your PhD. I also have one question. How do you combine the data from multiple cameras? Is when you detect a single person, is his ID identical in the next camera, or everything needs to start again from scratch?
Not yet. The unique ID for a single pedestrian is only for footage from one camera, but I've planned to add this feature because it helps us to improve our campus, especially when we can track maybe not every person, but let's say a lot of person from which point they are going to which point, and how to improve the facilities to make it more user-friendly.
So sounds like you have already implemented this approach, and it's actually in use in your university, isn't it?
I'm not yet, but I'm not yet implemented, but I'm already work on it.
All right. Thank you.
Thank you very much.
Okay, thank you, Pavel, for your presentation. We have to move on with the last presentation from Masters and Bachelors. It's Vasil Dimitrov from Architecture, Civil Engineering and Geodesy University in Sofia, Bulgaria. So, Vasil, can you hear us?
Hello, yes.
Yes, very good. Yes.
I hope you hear me well.
Yeah, it's good. So, if you're ready, we can start.
Yes, I'm ready. Hello, everyone. I'm Vasil Dimitrov, and today I have the pleasure to present you my master thesis with the topic creating a model of anomalous gravitational field based on GNSS measurements and gravimetry results. I'll start with the objective of my thesis, which is to conduct gravimetric and GNSS measurements, process and analyze the obtained results to identify an anomalous gravity field in the Zlatograd area here in Bulgaria, which will provide me a basis and a solid foundation for further research to understand the water resources in the area, particularly the groundwater. Through systematic collection and processing of gravimetric data, potential zones for groundwater discovery will be proposed, which will be a good basis for geophysical and geological studies after that, which will contribute to a better understanding of the underground structures in the Zlatograd region. A few words about Zlatograd. This is the southernmost town in Bulgaria, which is in the Rhodop Mountains. The town has focused on sustainable water resource management to preserve its natural environment and support local agriculture. The town relies on the Zlatograd Dam and its watershed for water supply, balancing consumptions with conservation. My thesis consists of a theoretical part, which examines the general principles of gravimetry and GNSS measurements, and the practical part where measurements were taken on a real object, and after that the results were made and the further analysis. I'll briefly outline the theoretical framework of my thesis, which is the inverse problem in the potential theory, where I can localize deep-seated anomalous masses under the physical ground, which is a specific case of solving this inverse problem. About the measurements that were made, so it was in October, from 27th of October until 21st of November 2023, where we had a total of 216 newly distributed points, and the average distance of the points were 400-500 meters. About the GNSS measurements, the chosen method for the geodetic fixing was GNSS with RTK mode using a virtual reference station. We used GeoVara infrastructure network, which guarantees a good coverage for the border regions, especially this one with Greece. The coordinates of the points were determined in BGS 2005 and with ellipsoidal heights. As you can see on the slide, I have provided some brief information about the BGS 205, which is used here in Bulgaria for all engineering applications, geodetic, cartographic, and etc. The two instruments which we used were the GNSS Tonex S900A and the gravimeter Lacoste and Romberg model G. This is a relative gravimeter. It's very important to clarify that, because with the relative gravimeter measurements, I can detect the differences in the gravity force, and after that, processing the results, I can receive the absolute gravity force value for all of the points. This is the scheme that we used for the gravimetric measurements, and also the gravimetric measurements in the Zlatograd region, which we used. So it was very important to have a point with a reference point, which was near the city of Kırjeli, used in International Gravity Standardization Network 1971 system. The data processing, so first is calibration of the gravimeter readings, after that applying the tidal corrections. Here they were calculated in MATLAB, obtaining the corrected values as the sum of the adjusted reading and the tidal correction, applying a correction for the zero drift of the gravimeter, calculating the gravimetric differences between the points and the final readings, and calculating the gravity force values for all these points. The models of the anomaly fields and gravity difference were created using the software Global Mapper and Surfer 8. All of the other softwares were, for example, Excel and MATLAB, which I mentioned. The free air anomaly, as you can see, this is the 3D model that I'm presenting to you. The blue zones here can be considered zones with gravity anomalies, where it's possible that the groundwater exists beneath the surface. About the Bouguer anomalies, here it's a bit different results because we are using different empirical data. And as a conclusion, I can say that based on the measurements taken and their subsequent processing, the relative gravimetric measurements combined with the GNSS determinations are a reliable source of empirical data that assist in the localization of anomalous masses located beneath the Earth's surface. The research process based on the results of relative gravimetric measurements combined with GNSS technologies should be proceeded in two stages. Firstly, to roughly identify the zones on the territory with anomalous gravity field. After that, to analyze and to see where the differences between the free air anomalies and the assumed gravity values allow us the creation of a model identical to the Bouguer anomaly field model, which can provide the basis to consider that if a correction with the assumed gravity values is applied to the free air anomaly, a field will be obtained that carries analogous information about the possible presence of water under the ground. Thank you.
Okay, thank you, Vasil.
Thank you.
So, is there a questions for Vasil? So, no questions at the moment for gravimetry. So thank you all finalists at the moment. We are done with your presentations, and now we have a slight delay of time, but anyway, we have a break until 4 o'clock Central European time, and now jury will go to another room to have a discussions, and hopefully we will start in time, so 4 o'clock. So take some break, some coffee or tea, and soon we will be back. Okay, see you.
Will you stop the recording?
Yeah, okay, we'll try.